The last 3 points on our agenda for today will tell us more on what we can actually do with VAR models. So let's start with so-called impulse response analysis. And consider again the example of the 3 variable VAR with inflation, unemployment, and interest rates. A natural question we could be interested in asking ourselves, for instance, is what is the effect on the entire system if we let the interest rate increase or decrease? This is a so-called what-if question. And in order to answer these questions, we would need to translate them into a mathematical device that we could use to provide an answer. Now, since the innovations, the error terms in our model contain all the news in the model, what we have not modeled, we would need to formalize these questions by shocking one of the error terms. For instance, the one corresponding to the interest rate, to trace out the effect of a sudden change in the interest rate on all other variables in the system. Now, the so-called impulse response functions exactly trace out these effects. They trace out the effect on current and future values of each of the variables in the system to, for instance, a 1 unit increase in the current value of one of the VAR errors. So in other words, you give a 1 unit impulse to one of the error terms in the model, and you trace out the response in current and future values of all other variables in the system. Now, this is, of course, a thought experiment where we will assume that the other errors are not affected and that the error we shock returns to 0 in the next period. So we trace out the effect of a temporary error. Now, how can we obtain these impulse response functions? Well, remember, we have seen earlier on a representation where we can express a time series in terms of a weighted sum of the past errors. This is exactly given by the moving average representation we have seen last week for AR models, but we can also get it for VAR models. Once we express our VAR in an MA infinity representation, we can read off the impulse response functions from the psi coefficient matrices over here. So the matrices in front of the lagged error terms. Just like in the regression framework, imagine that you give a 1 unit impulse or a shock to the error term of the jade variable at the right-hand side. Well, then the coefficients in the psi matrices tell you more about the expected effects in all other variables. So the ijade element in the psi matrix at lag S gives the effect of a 1 unit shock in the jade variable. So when you increase this one with 1 unit on the ith variable in your system of n variables, and this at horizon S. So now that we know how to read off the impulse response functions from the psi matrices, how can we compute the psi matrices? Well, to obtain the psi matrices, we need to rely on the same device that allowed us to re-express a VAR-P in the form of a VMA infinity representation to check the stability of the model. And that was our companion form. By recursive substitution, you can again show that these psi matrices are actually nothing more than the powers of the matrix F that popped up in the companion form. The reason why this J matrix pops up over here is because our F matrix is of larger dimension than n times n, and the J matrix just allows you to pick out the relevant upper left block in this matrix. Since the large error vector Vt over here is also a large vector where actually only the first part contains the error terms epsilon t as the relevant elements in the upper part. And it are these error terms that we need to shock in the upper block. So now that we know how to obtain the impulse responses, how can we do inference on the parameters? Then we would need to have standard errors. So is it easy to obtain standard errors around the impulse responses? Well, the psi's, the impulse responses, are nothing more than functions of the original AR parameters collected in the phi's. And we have seen that, well, you've seen in earlier courses that by the delta methods, we can very easily obtain the asymptotic variance of the impulse response parameters, which are functions of the original phi's. You just simply start from the asymptotic variance of the AR parameters, and then the delta method tells us that you can obtain the asymptotic variance of the psi's by simply pre and post multiplying by this matrix G, where the matrix G encodes the relations between the phi's and the pi's, namely through the gradient vector. In your tutorial assignment, you will learn how to obtain these impulse response functions and the asymptotic variance of the impulse response parameters in this question over here. Now, finally, how do impulse response functions look like in practice? Well, let us return to this 3-variable VAR system. And so for a VAR with 3, so n equals 3 time series, we have n squared impulse response functions. Since we can shock each of the n variables in the system and trace out the effect on each of the n variables in our system. So each of these impulse response functions are visualized over here through the solid black curve. So the impulse response function is a function that traces out the effects over time. What do we have in the first row? In the first row, we give a shock to inflation. So we look at inflation shocks. We give a shock to inflation and we trace out the effect on the other 3 variables in the system. In the middle row, we give a shock to unemployment. So when we look at unemployment shock, and we trace out the effects on the 3 variables in the system. In the last row, we look at a shock to the interest rate. Now, you not only see the impulse response function itself, but you also see these dashed lines around it, which are the confidence intervals. And if the 0 horizontal line lies inside of the confidence interval, well, then the corresponding effect at that particular lag is not significant. It's not significantly different from 0. And so based on this information from the impulse response functions and the confidence intervals, you can start interpreting them. We see, for instance, that a shock to inflation, so the top row, has a quite persistent effect on unemployment, as the effect is still significant after 24 periods. Now, before we end this section on impulse response functions, some final remarks here still. Until now, we've looked at the impulse response functions for the so-called reduced form VAR. That is the VAR I presented until now. But you often hear a critique on the impulse response functions. And what is this critique? Well, this critique has to do with a thought experiment behind impulse response functions. Remember, we shock a single error, we hold all the other constants, and we trace out the effect on the whole system. Now, this thought process only makes sense if all the error terms can indeed be kept fixed when one term is shocked. But remember, in our reduced form VAR, we had the multivariate white noise assumption that allows for instantaneous correlation between the error terms. So that seriously, of course, complicates the validity of our thought experiments, since if two errors are correlated, it's of course not possible that one of them is kept fixed while we shock the other. So for that reason, people turn to so-called orthogonalized impulse response functions, where the resulting error terms, the U's, are truly uncorrelated. And one way to obtain these is by deciding on an ordering of the variables and then including contemporaneous values of the variables corresponding to the previous equation in the model. So in the first equation, nothing is added. In the second equation, we have the contemporaneous value of y1 added. In the third equation, we have the contemporaneous values of the previous two guys added. So we order the variables where the first guy, y1, is allowed to contemporaneously affect the remaining ones, y2 and y3. And y2 is only allowed to contemporaneously affect the ones behind it, so y3. And of course, y3 can't contemporaneously impact anything anymore since it's ordered last. The impulse response functions that I've shown to you on the previous slide actually correspond to this so-called recursive VAR. And you can notice this since the IRFs start at non-zero above the diagonal, but at 0 below the diagonal. An alternative route to this critique can be defined by so-called generalized impulse response functions, where actually the correlation between the other errors is accounted for in this generalized impulse response functions approach. Now, another alternative route is to look at structural VARs, where economic theory is used to lay out a set of identification restrictions to arrive at the structural errors they use instead of the reduced form errors from before. Now, I've included these references here on the slide in case you're interested to know more about this, but in this course, we won't dive deeper into this material. Lastly, one final remark about the confidence intervals. The intervals we looked at are pointwise intervals. So for each impulse response coefficient corresponding to a specific lag on the horizontal axis, we construct a corresponding confidence interval. So we don't have a joint confidence band around the entire impulse response function. In case you would like to obtain such a band, you can resort to, for instance, bootstrap methods. And interested students can read more on this in this paper, for instance.